The MOSFET is the dominant form of transistor used today, and it's made possible our modern VLSI systems. More MOSFETs are manufactured in the state of California each year than raindrops fall on the state.
MOS stands for metal oxide semiconductor, which represents the MOS capacitor with an oxide insulator that forms the central part of the transistor. The first MOSFETs were made with metal gates, but some MOSFETs are made with a form of silicon called polysilicon. In either case, they're called MOSFETs. FET stands for field effect transistor, which means that the transistor effect is governed by an electric field, namely the electric field of the MOS capacitor. The MOSFET, shown here in schematic form, has two input voltages, the gate to substrate voltage and the drain to source voltage. These two voltages combine to determine the drain current ID. We typically use the transistor in digital circuits with the gate to substrate voltage as the control voltage. So by changing the gate to substrate voltage, we change the current through the transistor. We can build two flavors of MOSFETs, N-type and P-type. The N-type has N-type diffuse source and drains. The P-type has P-diffuse source and drains. Here's a cross-section of a MOSFET. We see the gate material and the oxide that separates it from the rest of the transistor. The drain and source are shown here. In this case, they're doped N, making this an N-type transistor. The center region holds the channel, it's P-type. We use the gate voltage to control the current between the source and the drain. The Fermi level throughout the bulk silicon is constant, but we use the gate voltage to control the bands in the valence and conduction regions. Here's a top view of the transistor. Here are the drain and the source. The channel is here, and the current in this case flows between the drain and the source. We put the gate material on top of the channel, of course with the oxide in between. The two most important parameters that a circuit designer can control are the width of the transistor and the length. The width is perpendicular to the direction of current flow. The length is along the direction of current flow. By changing the width and the length, we can change the current through the transistor. Of course, that can only be done at fabrication time. Typically in digital circuits, we use the minimum size length, so effectively the designer adjusts the width in order to control the amount of current that the transistor can produce. One interesting fact about the manufacture of these transistors is that you don't try to make the channel first and then hit the gate on top of it. Even a small gap between the gate and the source and the drain will cause the transistor to not work. Instead, we use what's called a self-masking process. First put down the gate and then put down the source and drain diffusions. The gate acts as a mask for the diffusions and protects the channel region. As a result, we get a nice clean boundary between the gate and the source and the drain and great alignment. Let's review some terms. Cox is the oxide capacitance. N sub I is the carrier concentration of intrinsic silicon, and capital N sub A is the doping concentration. So when we use this MOSFET, we're going to apply a gate to substrate voltage, and we're going to apply a drain to source voltage. The gate to source voltage will cause minority carriers, in this case N-type carriers, to be attracted to one of the plates of the MOS capacitor. That will allow current to flow between the source and the drain, giving us the drain current ID. Now we want to find a model that describes the relationship between the gate to source voltage, the drain to source voltage, and the drain current. First thing we need to understand is the threshold voltage. The transistor does not conduct at all below the threshold voltage. We can derive a formula for the threshold voltage that depends upon several parameters. It depends upon temperature, it depends upon the bias voltage of the substrate, depends upon channel length, and also depends upon drain voltage and several other physical effects. We need to know the mobility of the carriers in the channel. Although classical physics theory tells us one value for the mobility in the channel for the carriers is lower than that in bulk silicon because of a variety of physical effects. That value is independent of doping, substrate bias, or the gate oxide thickness. But it is difficult to physically model. As a result, it's usually measured. We use the transconductance K prime to describe the transistor's ability to produce current. K prime is the product of the effective mobility and the oxide capacitance. It's in units of microamps per volt squared. So it relates the output current, the drain current, to the gate voltage, making it a transconductance. We can see that increasing the gate capacitance increases the transconductance. Now let's build our simple current voltage model for the transistor. It has two different regions of operation. In the linear region, the drain to source voltage is less than the difference between the gate to substrate voltage and the threshold voltage. In this case, the drain current depends upon both the gate to substrate voltage and the drain to source voltage. In the saturation region, which is on the other side of the relationship between VGS minus VT, the drain current still depends upon the gate to substrate voltage, but it's independent of the drain to source voltage. That's why we call it saturation, because we don't get more current by increasing the drain to source voltage. You can see in these equations that the current depends upon the ratio of the width to the length. So making the transistor wider gives us more current. This makes sense because we have more area with more carriers. We can plot this simple model. The x-axis is the drain to source voltage, the y-axis is the drain current. And we'll draw several curves, one for each value of gate to substrate voltage. Below the threshold voltage, the transistor does not conduct. I sub D is 0. At the threshold voltage, we get a small current. As we increase the gate to substrate voltage, we get a larger current, and we can see that the current saturates once the drain to source voltage goes beyond a certain value. Further increasing the gate voltage gives us more increase in the drain current. Here's the boundary between the linear and saturation region. We can see that it moves out as a function of gate voltage. Why does the saturation region exist? It's because of a physical effect in the structure of the inversion region. If we have a low VDS, the minority carriers are spread evenly throughout the channel. As we increase VDS, we have more carriers at one end of the channel at the other. As we increase VDS, the depth of the inversion region becomes narrower at one end of the channel. As we further increase it, we eventually reach what's known as the pinch-off point, at which the inversion region can become no thinner. The current saturates at the pinch-off point.
Of course, our assumption that the drain current drops immediately to 0 as soon as the gate voltage drops below the threshold is a simplification. In fact, drain current continues to flow even at sub-threshold gate voltages. This subthreshold current is an important source of power consumption in modern VLSI systems.
The inversion charge in the channel depends exponentially on VG, so the subthreshold current drops off quickly, but it does exist. We can develop a rather complicated formula for the subthreshold current. You can see that it depends upon temperature and it depends upon doping, but it is independent of many of the device parameters. Here's a plot of the drain to source voltage versus the drain current around the subthreshold region. It has two components, a drift component and a diffusion component that combine to form the total subthreshold current. The slope of this curve is known as the subthreshold slope, and it's an important parameter for characterizing the subthreshold operation of the transistor. The subthreshold slope is known as S. It's defined as 1 over the derivative of the ratio of the log base 10 of the drain current to the gate voltage. S depends upon the ratio of the bulk depletion capacitance to the oxide capacitance. We want the subthreshold slope to be large because that means that the subthreshold current drops off quickly as we go below the threshold voltage.
The MOSFET combines an MOS capacitor with source and drain regions. As a gate voltage is applied, an inversion layer is formed, allowing current to flow between the source and the drain. The device characteristics relate the drain current to two voltages, the gate to substrate voltage and the drain to source voltage. The drain current has two regions, one the linear region in which the drain current depends upon the drain to source voltage, the other the saturation region in which the drain current is independent of the drain to source voltage. Subthreshold slope characterizes the rate at which subthreshold current falls as the gate voltage decreases.
The subthreshold slope is defined as the derivative between the log of the drain current and the gate voltage. And it depends upon the ratio, and it depends upon the subthreshold slope is known as S. It's defined as the derivative of the ratio between the subthreshold slope is known as S, and it's defined as 1 over the subthreshold slope is known as S, and it's defined as 1 over the derivative of the log 10 of the drain current as a function of gate voltage. S depends upon the ratio of the bulk depletion capacitance to the oxide capacitance. We want a large subthreshold slope because that means that the subthreshold current drops off faster as we get below the threshold voltage. The subthreshold slope is known as S, and it's defined as 1 over the subthreshold slope is known as S. It's defined as 1 over the derivative of the ratio of the log base 10 of the drain current to the gate voltage. S depends upon the ratio of the bulk depletion capacitance to the oxide capacitance. We want the subthreshold slope to be large because that means that the subthreshold current drops off quickly as we go below the threshold voltage.